Okay, we're on section 27.2, resistors in series and parallel. We'll start with the series resistors. If you look at the figure at the bottom, you see a pictorial representation of two resistors connected in series to a battery. Now they've got light bulbs, but they are resistors basically. So if you look, there's really only one path. So even though they have the labels I1 and I2 going through the light bulb 1 and light bulb 2 and going through R1 and R2, it really is all the same current. So I equals I1 equals I2, and in the final equivalent circuit, you see that it's just in a series circuit. You just have the addition of the two resistors. So when you have a series circuit like this, the current is the same in the entire branch. So the current that's coming out of the battery is going through the resistors, is coming back to the battery. It's all I1. Now, I'm sorry, it's all I. It's all the same current, I. Now, the voltages are going to be different. And we'll look at that. The voltages, delta V is equal to delta V1 plus delta V2. How do you determine delta V1 and delta V2? Well, you can take a little voltmeter and measure it. That's one way, but knowing the current through the circuit, if you have an ammeter, or just calculating, knowing the battery voltage delta V, you have the current times resistor 1 will give you delta V1, and the current times R2 will give you delta V2. Now, the current in this case is the same. I1 and I2 are equal. They're both equal to I, so you can, using the distributive property, you can take out I. So it's I open paren R1 plus R2 close paren. So the resistance is just R1 plus R2. That is your equivalent. So delta V equals I times R equivalent. So to get in a series circuit, the R equivalent is equal to the sum of each of the resistors, R1 plus R2 in this case, but if you have more, then it's R3 plus R whatever, Rn. Okay, a quick quiz. With the switch in the circuit of the top figure, closed, there's no current in R2 because the current has an alternate zero resistance path. In other words, it's a short. There's a short going across R2 through the switch. There is current in R1, and this current is measured with the ammeter at the bottom of the circuit. If the switch is opened, there is now current in R2. What happens to the reading on the ammeter when the switch is opened? Well, you had one current with R1. Now you've just added an additional series resistor. So if V is equal to, if I is equal to V divided by R, and R increases, the current is going to decrease. So the reading is going to go down. Okay, now resistors in parallel. Now here we have, you can see the two light bulbs are they're connected, and then they're connected. This is the way Christmas lights, if the Christmas lights were connected in series, once one light bulb goes out, the whole chain would go out. But if you take out one bulb, the other bulb will stay lit, or the other bulbs in a string of Christmas lights. So they should be wired in parallel. And this is the middle figure is the equivalent circuit. Is the circuit drawn. So you have the voltage coming out, and that voltage is the same across R1 and R2. So in a series circuit, you have one current but multiple voltage drops. In a parallel circuit, you have one voltage across the devices but multiple currents. So series, one current, multiple voltages. Parallel, one voltage, multiple currents. And you'll see that in the third, and we'll get there, the R equivalent, the reciprocal of the R equivalent is 1 over R1 plus 1 over R2. So let's look at this. So delta V equals delta V1 equals delta V2. So the voltage is the same across those resistors. So now the current, I is equal to I1 plus I2, and the delta V1 divided by R1 will give you the I1, and delta V2 divided by R2 will give you the I2. Well, since delta V1 equals delta V2, that's equal to V times 1, open paren, 1 over R1 plus 1 over R2, close paren, and that's how we get, they don't show the distributive property here, but if you pull out delta V, which is equal to delta V1 and delta V2, you get delta V times, in parentheses, 1 over R1 plus 1 over R2. So when you have resistors in parallel, the 1 over R equivalent is equal to 1 over R1 plus 1 over R2. Now, I've given you that little shortcut where, please remember that this is 1 over R equivalent. This is not the answer to your equivalent resistance. You have to take the reciprocal of this to get the equivalent resistance. And if you only have 2 resistances, then you can use the R1 times R2 over R1 plus R2, and that'll give you the equivalent resistance. So to calculate an equivalent resistance, it's 1 over R equivalent equals, I don't know why they have it twice there, equals 1 over R1 plus 1 over R2 plus 1 over R3. If you have more than 2, you can't use the little shortcut R1, R2 divided by R1 plus R2. You just have to brute force it. But remember, you need to take the reciprocal when you get the final answer. Okay, quick quiz. With the switch in the circuit of the top figure open, there's no current in R2. There's current in R1, and it is measured with the ammeter. If the switch is closed, as shown in the bottom figure, there's current in R2. What happens to the reading on the ammeter when the switch is closed? The reading increases, the reading decreases, or the reading does not change. Well, one thing I failed to mention, whenever you have resistors in parallel, the equivalent resistance is always less than the lowest resistor in the network. So your resistance is going to go down. The total resistance, R equivalent, is going to go down. So the V divided by R, if R goes down, then the current has to go up. So the reading increases. Okay? The less resistance means more current. Wider hose means more water going through it. All right. In the figure, a third resistor is added in series with the first 2. What happens to the current in the battery? You're adding more resistance, so the current is going to decrease because, again, V divided by R, if the R increases, if you add another resistance, the current decreases. What happens to the terminal voltage of the battery? Well, the drop across the if you're drawing less current, it's actually going to increase. The terminal voltage will increase because you're drawing less, you're having less of a current draw on it. Okay, in a figure, a third resistor is added in parallel with the first 2. What happens to the current in the battery? Well, basically, you've just given a third path for more current. So the current has to increase. It increases. Okay, what happens to the terminal voltage of the battery? Well, by the same token that on the previous one in the series, it increased, here it's going to decrease. And we'll stop there and go on to Kirchhoff's rules.